Let me ask you something. Have you ever actually stopped to think about gravity? Not just the word, not just the vague idea that things fall down, but really thought about what it is, how it works, and whether everything you learned about it is actually true. Because I'm going to be honest with you, most people walking around right now, including a lot of people who did well in school, who consider themselves scientifically literate, have a mental picture of gravity that is either incomplete, misleading, or just flat out wrong. And today we're going to fix that. We're going to start from scratch, tear apart the myths one by one, and by the end of this video, you're going to see this invisible force that rules your entire life in a completely different way. Let's start with the story everyone gets told. Isaac Newton. An apple falls from a tree. Suddenly gravity is discovered. You've heard it 100 times. It's in textbooks, it's in cartoons, it's practically a cultural shorthand for the moment of scientific insight. But here's the problem. That story is deeply misleading, because Newton did not discover that things fall. Humans have known things fall since before we could write. Rocks fall. Rain falls. People fall. This was not a mystery that needed solving. What Newton actually did, what made him arguably the greatest scientist who ever lived, was realise something that nobody before him had ever connected. He realised that the force pulling the apple toward the ground is the exact same force keeping the moon in orbit around the Earth. Think about how insane that is. The moon is nearly 400,000 kilometres away. It's travelling through the vacuum of space. And Newton looked at that and said, that's the same thing as this apple. The moon is essentially falling toward Earth constantly, but moving forward fast enough that it keeps missing. That's what an orbit is. It's a continuous free fall where you keep missing the thing you're falling toward. Newton didn't discover gravity. He discovered that gravity is universal, that it operates across the entire cosmos, between every object that has mass, across any distance at all. And he described it with an equation so clean and powerful that it predicted the motion of planets, the path of comets, the behaviour of tides, and the trajectory of cannonballs, all with the same formula. For over 200 years, that equation was one of the greatest intellectual achievements in human history. But here's what Newton himself admitted, and this is something almost nobody talks about. He had absolutely no idea why gravity worked. He could describe it. He could calculate it with breathtaking precision. But the actual mechanism, what is gravity? What is it made of? How does it reach across empty space and pull on things? He had no answer. He famously wrote that he would feign no hypotheses. He wasn't going to guess at what was happening underneath the math. And so for over 2 centuries, we had this perfect description of something we fundamentally did not understand. That changed in 1915 when Albert Einstein published his general theory of relativity. And this is where the biggest misconception of all comes in, because Einstein didn't just refine Newton's picture of gravity. He completely replaced it with something that barely resembles it at all. According to Einstein, gravity is not a force. Let me say that again clearly because it's worth sitting with. Gravity is not a force. It doesn't pull on things the way a magnet pulls on iron, or the way a rope pulls on a boat. What gravity actually is, according to general relativity, is a curvature in the fabric of space-time itself. Now, space-time is the 4-dimensional structure that combines the 3 dimensions of space with the dimension of time into a single, unified thing. And Einstein said that massive objects, planets, stars, anything with mass, warp and curve this fabric around them. The more massive the object, the more severe the curvature. And other objects moving through this curved space-time don't get pulled in some mystical way. They simply follow the natural contours of the geometry around them. They're taking the straightest possible path through a curved space, and that path curves around massive objects, which is what we observe as gravitational attraction. The classic way to picture this is to imagine a stretched rubber sheet, like a trampoline. Place a heavy bowling ball in the centre, and the sheet sags and curves around it. Now roll a marble nearby. The marble curves toward the bowling ball, not because some invisible hand is grabbing it, but because it's following the slope of the sheet. That's gravity, not a pull, a curve, a geometric feature of reality itself. And this isn't just a more complicated way of saying the same thing Newton said. It makes different predictions, and those predictions have been tested and confirmed over and over again. The way light bends around massive objects, the precise drift of Mercury's orbit that Newton's equations couldn't fully explain, the existence of gravitational waves, ripples in the fabric of space-time that we only directly detected for the first time in 2015. All of it confirmed Einstein's picture. Gravity is geometry. Now here's one that surprises almost everyone. Gravity, the force, or rather the phenomenon, that holds galaxies together, that formed every star and planet in the universe, that keeps your feet on the ground, is by a ridiculous margin the weakest of all the fundamental forces. We're not talking slightly weaker, we're talking incomprehensibly, almost laughably weaker. The electromagnetic force is roughly 10 to the power of 36 times stronger than gravity. That's a 1 followed by 36 zeros. The strong nuclear force, which holds atomic nuclei together, is even stronger than that. And yet gravity is the one that dominates the universe on the largest scales, and people find this deeply confusing. The reason is actually pretty simple once you hear it. Gravity has two properties that the other forces don't share in the same way. First, it has infinite range. It weakens with distance, but it never fully disappears. No matter how far apart two objects are, there is still a gravitational attraction between them. Second, and more importantly, gravity only attracts. It never repels. There is no negative gravity. The other forces, like electromagnetism, come in two varieties, positive and negative. Or in the case of the nuclear forces, different charges that can cancel each other out. Over large scales, these forces tend to balance and neutralize. But gravity just keeps accumulating. Every bit of mass adds to the gravitational pull, ERT. So while a tiny fridge magnet can effortlessly beat the gravitational pull of the entire planet Earth when it holds a piece of paper to your refrigerator door, and yes, the magnet genuinely wins that contest, gravity wins at the scale of galaxies and beyond, because it never cancels and never stops. Here's another one that messes with people's heads. You think you feel gravity right now. You feel the weight of your body, the pressure of the chair or the floor beneath you, and you attribute that to gravity pressing you down. But that's not quite right. What you're actually feeling is the floor pushing up. Gravity isn't something you can feel in the same way you feel a push or a shove. In true free fall, jumping from a plane before the parachute opens, or floating inside the International Space Station, you feel completely weightless. Not because gravity is gone. In the ISS, gravity is still around 90% as strong as it is on the surface of the Earth. You feel weightless because nothing is pushing back against you. You're following the natural curve of space-time freely, without anything resisting you. The sensation we call weight is actually the sensation of being prevented from following that natural path. The ground is constantly shoving you upward, away from the path you'd naturally take through curved space-time, and that resistance is what you feel. This connects to one of Einstein's most profound insights, something he called the equivalence principle. He pointed out that if you were in a sealed box in deep space, being accelerated upward at exactly 9.8 meters per second squared, it would feel completely identical to standing still on the surface of the Earth. You couldn't tell the difference from inside the box. Gravity and acceleration are, in a very deep and real sense, the same thing. This single observation was the seed from which all of general relativity grew. And then there's time. This is the one that really breaks people, because we intuitively feel like time is this steady, universal drumbeat ticking at the same rate everywhere. But it isn't. One of the stranger predictions of general relativity, a prediction that has been confirmed experimentally, is that gravity slows down time. The stronger the gravitational field you're in, the slower time passes for you relative to someone in a weaker field. This is called gravitational time dilation. And it's not a theoretical curiosity, it's a real measurable effect. Your feet right now are aging fractionally slower than your head. Because they're closer to the Earth's centre of mass, deeper in the gravitational well, time ticks just a tiny bit slower for them. The difference in a human lifetime is too small to ever notice or measure with any practical tool. But take that effect and scale it up to something like a neutron star or a black hole, and it becomes enormous. Near a black hole's event horizon, time as experienced by an outside observer appears to slow to a crawl. For an object falling in, time continues normally. But enormous stretches of time pass in the outside universe. This isn't science fiction. GPS satellites experience this effect every single day. The clocks on GPS satellites run fast by about 38 microseconds per day compared to clocks on the ground, because the satellites are higher up in Earth's gravitational field, where space-time is less curved. If engineers didn't account for this and correct for it constantly, GPS positions would drift by about 11 kilometers every single day. Relativity isn't abstract philosophy, it's embedded in the technology in your pocket. And yet, after all of this, after Newton's universal gravitation and Einstein's curved spacetime and gravitational waves and time dilation, we still do not have a complete theory of gravity. Einstein's general relativity works spectacularly well at large scales, but zoom down to the quantum world of atoms and particles, and the theory breaks down completely. Quantum mechanics, the framework that describes everything at the subatomic level, is fundamentally incompatible with general relativity. Every other fundamental force has been successfully incorporated into the quantum framework. Electromagnetism, the strong nuclear force, the weak nuclear force, all unified. Gravity stands alone. Despite nearly a century of effort by some of the most brilliant minds in physics, nobody has successfully built a quantum theory of gravity that works. And that's before we even get to dark matter, the invisible, undetected substance that appears to account for most of the mass in galaxies, inferred entirely from its gravitational effects because we've never directly observed it. Or dark energy, even more mysterious, a property of space itself that's causing the expansion of the universe to accelerate, working in some sense against gravity on the largest scales, and about which we understand almost nothing. Gravity is the oldest force we recognized. It's the most immediately, viscerally present force in our daily lives. It shaped every structure in the universe, from the smallest asteroid to the largest galaxy cluster. And in many ways, it remains the deepest mystery in all of physics. The more carefully you look at it, the stranger and more wonderful it becomes. So the next time you feel your feet on the ground, just remember, that sensation isn't gravity. It's the universe pushing back. If this changed how you think about something you felt every second of your life, hit like and subscribe. I want to know in the comments, which part of this surprised you most? Was it that gravity is the weakest force, that time slows down? Or that after all this time we still don't fully understand it? Drop it below. See you in the next one.